Today's lesson is going to be a consolidation lesson for grade 11 chemistry. The key concepts that we're going to be having a look at is types of chemical reactions, chemical bonding, then we'll have a look at some chemical calculations, and finally at chemical systems. Now I'm going to start by talking to you guys a little bit about the different types of reactions that we need to be able to identify. Right, so when we look at a chemical reaction, we need to be able to see what is happening here. Is something adding into the equation? It could be addition. Are two things coming together? It could be elimination. So let's start off by just listing our different types of reactions and talking about each of them. The first and probably the easiest one to recognize is a redox reaction. Remember, in a redox reaction, we have got both oxidation and reduction taking place. So the oxidation numbers change. Something gets oxidized and something gets reduced. So oxidation and reduction, and that involves electron transfer. Let's just have a look at the different things that we need to know about a redox reaction. Okay, so something gets oxidized. When oxidation takes place, it involves a loss of electrons, resulting in something having a bigger oxidation number because it's lost some of the negatives. When, in the case of reduction, it involves a gain of electrons. So first type of reaction, a redox reaction, I think relatively easy to identify. The next reaction that we need to be able to identify is an acid-base reaction, also in some cases called a neutralization reaction. Acid-base reaction or a neutralization reaction. Now, in an acid-base reaction, unlike a redox reaction, there's no change in the oxidation numbers, and let's have a look at a typical example. Typical example would be something like hydrochloric acid reacting with sodium hydroxide. So hydrochloric acid has a pH of less than 7 and sodium hydroxide with a pH of more than 7. Now what we're going to do, put them together and neutralize. So when an acid reacts with a base, we always get a salt and water. And the salt which we're going to get in this case is sodium chloride. Now an acid-base or a neutralization reaction doesn't necessarily have to take place between an acid and a base. It can also take place between an acid and a carbonate. Now, if a neutralization reaction takes place between an acid and a carbonate, instead of just getting salt and water, we will get salt, carbon dioxide, and water. So salt, CO2, and water. Right, next type of reaction is called an elimination reaction. Now, the word elimination actually already gives us a clue as to what happens. Now, in an elimination reaction, let's have an example. I'm going to use in an elimination reaction, what happens is something is taken off of our compound. So let's say, for instance, I had an OH over here and a hydrogen over here. This is an organic compound, of course, because it contains carbon, hydrogen, and oxygen. I could do something to this reaction to make the OH and the H eliminate themselves from the compound and then end up with a double bond instead. So an easy way, in a way, to identify an elimination reaction is to say, if I've got one thing on the left and two things on the right, that could possibly be elimination. Let's have a look at the next. Well, the opposite of elimination is then addition. And a good example of an addition reaction would be if I take a compound like ethene and I add something to it, like HCl, for instance. What happens now is I've got two things on the left-hand side, but on the right-hand side, I'm only going to have one thing because the double bond in between the two carbons is going to break. One of the carbons is going to accommodate the hydrogen, and the other carbon is going to accommodate the chlorine. So I've added something new to this compound, therefore making it an addition reaction. Then there's also substitution. So substitution in sport, if a substitute comes onto the field, then the substitute will take the place of somebody else. Now, that's exactly what happens in a substitution reaction as well. If I've got something like, this is actually methane, adding HCl to it, and then the chlorine can take the place of one of the hydrogens, let's say that one. So it's substituting for the hydrogen, and I'm left with H2. Okay, so let's run through them again quickly. Redox reaction. Best way to identify, look for a change in oxidation numbers. Remember, with a redox reaction, there has to be, something has to get oxidized, something has to get reduced. There has to be an oxidizing agent, there has to be a reducing agent. It involves the transfer of electrons. So if a substance is getting oxidized, it will become more positive. If it is getting reduced, it will become less positive or more negative. Then there's the acid-base reaction, or a neutralization is probably a better name. That generally takes place between an acid and a base, or between an acid and a carbonate. We take two things with pHs on opposite scales of our pH scale, we put them together, they neutralize each other, and I end up with something with a relatively neutral pH. So that is an acid-base or a neutralization reaction. An elimination reaction, something goes, I start with one thing, and I end with two things. So I start with one thing, end with two things. Addition reactions start with two things, end with one thing. Right, so that's the elimination and the addition. And then there's also the substitution reaction, which the last one is an example of. Right, now let's have a look at the questions on types of reactions and see whether we are able to handle them with ease. Right, the first question says, identify the type of reaction in each of the following examples. Now, if you have a look at our reactants, NaOH is a base. HCl is a acid. Add the two together and I end with NaCl, which is a salt, and water. And that definitely tells me that my first reaction is a neutralization reaction. Neutralization. Easy one to spot as long as you know what you're looking for. Okay. Now the next reaction is actually one that I haven't particularly spoke about earlier on, so I'm very glad that this example is here. So what do we have over here? I've got HCl in water. So it's an acid in water. Now that's not a neutralization reaction because water is neutral. It doesn't have the power to neutralize HCl. On the left-hand side, I've got HCl and H2O, and on the right-hand side, they have turned into ions. They have ionized, because remember, that's exactly what an acid does. It donates one of its protons to water to give us H3O+. So the next reaction is an ionization reaction, because ions are formed during the course of the reaction. Ionization. Right, on to example C. Now for me, it is very obvious that C is a redox reaction. And I'll tell you guys how I see it. Say to myself, wait a minute, copper on the right-hand side is on its own. On the left-hand side, copper is in a compound. Hydrogen on the left-hand side is on its own. On the right-hand side, it is in a compound. So they haven't just swapped positions. The fact that it's on its own in one place and that it's in a compound in the other definitely means that there has to be a change in oxidation numbers. And the only way that I can change oxidation numbers is by transfer of electrons. So let me show you guys what I mean. Oxygen, when it's in a compound, has got a charge of 2-, meaning that when copper is bonded to oxygen, the copper on the left-hand side has got an oxidation number of 2+. Then, on the right-hand side, copper is on its own. It's not bonded to anything, so its oxidation number is 0. What has happened to copper? It has been reduced. So it gained 2 electrons, and it got reduced to copper. Now, if something is reduced, something needs to get oxidized. And in this case, it's hydrogen that gets oxidized. Let's take a different color pen. H2 turning into H2O. H2 on its own, oxidation number 0. Hydrogen bonded to oxygen, oxidation number 1+. So definite transfer of electrons going on here. Very easy to see, really. This is definitely a redox reaction. Right, let's move on to equation D. And let's see what's happening over here. We've got C3H6 and bromium giving us C3H6 with bromium on it. Now, this is definitely an addition reaction because I started with 2 things on the left-hand side and I ended up with 1 thing on the right-hand side. So because it's so much fun, let's draw out this reaction properly. So I'm going to draw C3H6. C3H6 is a compound called propene. It contains 3 carbons. Right, now I'm going to put, it'll have to contain a double bond. Now you guys are in grade 11, you might not have done the organic chemistry behind this. So don't stress out if you can't do this drawing. You will learn how to do it next year. I'm just showing you out of pure interest. Right, so I've managed to draw 3 carbons and 6 hydrogens. Now, what is going to happen over here is when I add the bromium, one of these double bonds is going to break, and I'm going to have like 2 extra arms that are stuck out, and that is where those bromiums are going to sit. So my end result will be my 3 carbon chain, a bromium on each of those carbons, but instead of the double bond, there's now only a single bond. So what has happened is that bromium has added to this compound. And this is something that you're going to learn quite a lot about next year, because bromium, what would happen visually in this reaction, let's put it that way, is you would take your compound called propene and you would bubble it through water that contains bromium. Now, water that contains bromium will have a reddish brown color. Now, the fact that the double bond on the propene breaks and it adds the bromine out of that bromine water will let the water change from a reddish brown color to eventually colorless. So then we just need to fill in our hydrogens over here. So very, very definite. Now, D is an addition reaction. The next question asks us to state whether the following reactions take place spontaneously or not. So let's quickly just talk about what is a spontaneous reaction. If a reaction takes place spontaneously, then when those two reagents are placed together, the reaction will proceed naturally without us having to do too much to help the reaction along. If a reaction does not take place spontaneously, it means that energy needs to be added to the system in order to make the reaction take place. So the easiest way to see whether a reaction is spontaneous or not is to consult your your standard electrode potential. So let's have a look at the first one. The first one, I've got fluorine reacting with potassium chloride to give me potassium fluoride and chlorine. Now, what I'm going to do is I'm going to look at the fluorine and I'm going to look at Cl minus. I am not concerned with the potassium. The potassium is merely a spectator. You guys can see that it doesn't change much from the one side of the reaction to the other. So you identify, the first thing that you do is you identify the role players in your reaction by looking at the guys on the left-hand side. Now, you take your standard electrode potential table and you're going to look those guys up on your standard electrode potential table, and based on where they appear will tell you whether the reaction is spontaneous or not. Now, it sometimes takes a while to find things on here, but I've already made a bit of a circle around fluorine. It's right at the bottom, and then Cl minus is on the right-hand side and at the top, right? So there's Cl minus, right-hand side at the top. Here's Fe2, left-hand side at the bottom. Now, whenever you have what I call a top right, bottom left situation, your chemical reaction will be spontaneous. So let's just talk about the method again. You identify the role players. You take your highlighter and you highlight them on your half reaction table and you say, the guy on the right must be at the top, the left-hand one must be at the bottom. It will be spontaneous. If it's the other way around, left top, right bottom, then it's a non-spontaneous reaction. Okay, so let's just check again. There's Cl minus, there's Fe2. I've got a top right, bottom left situation, so very definitely this first reaction is spontaneous. Let's just write that in. Spontaneous, yes, check. Okay, now let's have a look at the next one. In the next one, we've got iodine reacting with lithium chloride to give us lithium iodide and chlorine. Now, this reaction is not spontaneous. I'm going to consult my half reaction table again, and let's just quickly have a look. Now, my role players in this one will be I2 and Cl minus. Right, so let's have a look and see if we can find these guys. I2, Cl minus I've already found just now. There it is. I2 is much further up on the half reaction table. So what I've got here is a top left, bottom right situation, and a top left, bottom right situation means that it is not spontaneous. So this second reaction is definitely not spontaneous. Right. Now what you will do is you will employ similar methods for C and D still remaining. You will check their positions on the half reaction table, and you will make sure, and you will base your decision based on the top right, bottom left situation. Okay, now when you look this one up on the half reaction table, you find that it is actually spontaneous. Let's just check it one more time because we already know where Cl is. So we're going to be having a look at chlorine and Br minus. So chlorine and Br minus. Right. Chlorine is over here on the left hand side, and let's just search the table for bromium. Can't be far, but it's sometimes difficult to find. It's probably just easiest to systematically go through the whole list like this. Ah, there it is. It's not even far away. I should have looked closer because, of course, both bromine and chlorine are halogens, so they can't be too far apart. And I've got a top right, bottom left situation going on, and that means that definitely these reactions, this reaction is spontaneous. So let's put that in. All right, once again for the last one, D, I've got a top right, bottom left situation, so reaction D is also spontaneous. Let's just tick it. Okay, so in order to find out whether a chemical reaction will occur spontaneously or not, in other words, to find out if I need to add energy to the system to make it happen or not, you will consult your half reaction table. Identify your role players on the left-hand side, okay? And you have to write it in ionic form, like LiCl is not going to be on the half reaction table. However, Cl minus is. And I can see the reason I choose Cl minus and not lithium is because lithium is merely a spectator. It is not undergoing any change in this chemical reaction. So you identify those role players on the left, you take out your half reaction table, which you should be given with every test that you write, and if you've got a top right, bottom left situation, then you know that it's spontaneous, otherwise not. Right, let's move on to the next question. The next question asks us to identify whether the following are redox reactions or not. Okay. Now what we're going to do is we'll have a look at them, we'll see which ones are redox, and we'll try and identify the other types of reactions as well, just for the fun of it. Okay. In reaction A, I have got copper sulfate reacting with H2S, hydrogen sulfide, very poisonous, giving me CuS and H2SO4. Now, remember what I said to you guys earlier, how we identify a redox reaction. A redox reaction involves transfer of electrons, and usually in a redox reaction we will have something on its own and now it's in a compound, or now it's in a compound and then it's on its own, indicating to us that there must have been some sort of an electron change. This one does nothing of the sort. If I do this, if I say copper sulfate and I underline that in pink, and hydrogen and sulfur over there, underline that in pink. If I underline them on the right hand side, there's my sulfur, there's my hydrogen, and in pink here's my copper, there's my sulfate. So all that has happened here is they have swapped places. One thing has swapped places with another thing. There's no evidence to support that, that it's a redox reaction. This will be a substitution reaction. Another quick check is just to see. Sulfate has got a has got a charge of 2 minus. So if it's 1 copper bonded to a sulfate, it must be 2 plus. The same with S. So now, nothing has happened here. It's just, well, something has happened, but nothing along the lines of transfer of electrons has happened. So the first reaction, we will say, is a substitution reaction. Right, let's have a look at reaction B. Now, reaction B looks a lot more like it could be a redox reaction. Just intuitively, here copper is on its own, now it's in a compound. Definitely something must have happened to the oxidation number of copper to enable it to go from 0 to in a compound. Because if it's in a compound, because it's a metal, it'll be positive. So this is most definitely a redox reaction. And let's just identify the role players here. So redox. Right, what has happened to copper over here? It's on its own, so its oxidation number is 0. Over here, it is bonded to sulfate, so its oxidation number is 2 plus. Copper sulfate, by the way, is a beautiful blue color because of the copper 2 plus. Copper 2 plus ions is a lovely, lovely blue color. Now, what has happened to copper? Copper was oxidized. It was oxidized. It must have lost 2 electrons to enable it to get to copper 2 plus. Now, that must mean that something else around here has been reduced, and the compound that is reduced is the S. Right, so definitely transfer of electrons going on here. Reaction B is a redox reaction. Let's have a look at the next one. Again, I don't see any of the telltale signs of a redox reaction. It's just a whole lot of swapping going on here. So reaction C is definitely not a redox reaction. And in fact, reaction C and reaction D are so similar that I might as well do them at the same time. Na2SO3 and then Na2CO3, this one is also not a redox reaction. Now, just looking back quickly, you guys see that it's actually very easy to identify the one that is the redox reaction. Right, let's have a look at question 1.4. Question 1.4 says, give one term for each of the following descriptions. And the first description is a substance that donates electrons. Okay. Now, a substance that donates electrons is going to get oxidized, right? Because it's getting rid of its negatives, so that substance gets oxidized. But gets oxidized isn't a name. So what I'm going to say is that it is a reducing agent. Okay, I just don't think gets oxidized would have been quite acceptable. But remember, whatever gets oxidized is the reducing agent, and whatever gets reduced is the oxidizing agent. So substance that donates electrons is a reducing agent. The next question, a substance that accepts electrons. So a substance that accepts electrons is now doing exactly the opposite from the previous one. So this one must be an oxidizing agent. Oxidizing agent. And then finally, quite out of the blue, a solution of known concentration. So a solution of known concentration means it is a solution that we made ourselves. We measured off how many grams of whatever reagent. We know the volume of water that we used. And such a solution, of course, can be used in a titration. But a solution of known concentration is called a standard solution. Standard solution. Right, so quick one-word answers to those descriptions. Let's move on to question 1.5. Complete the following by giving the balanced chemical equation for each reaction. Okay? And for the first one, they've actually got to tell us what sort of a chemical reaction we must be looking at, because there's only one reagent on the left-hand side. So fortunately, they're quite nice about it, and they tell us that this is an elimination reaction. Now, whenever we're dealing with an elimination reaction, something obviously has to be eliminated from the reaction, and very often, guys, it's water. And water is eliminated as follows. By taking an O, by taking a hydrogen from, let's say, one of the carbons, and by taking an OH from another carbon, because that O and that OH is going to make up the water. Elimination reactions have to be triggered somehow. The elimination doesn't just spontaneously happen, and very often we use sulfuric acid, especially if we want to remove water, because sulfuric acid is a dehydrating agent. Right, now this molecule is symmetric, so it doesn't make any difference whether I take the H off this carbon or whether I take it off the last carbon. So let's just do this. If you want to, in some ways it is actually quite nice just to draw the full structure, because then that gives you a very nice idea of what happens. Okay. Carbon bonded to an OH, bonded to a hydrogen, and another carbon, and 3 hydrogens. Okay, so because of the presence of some dehydrating agent catalyzing this this reaction, the H and the OH will now be removed, and they will give me water. And the rest of the compound, let's just write it in shorthand now, so it will be CH3. Sorry, rather, no, if I'm taking it from that side, it will be, let's draw it. It's actually just easier in most cases to have a visual tool. So what's going to happen is this first carbon is now only going to have 2 hydrogens on it. Fine, because the one is gone. The second carbon has lost the OH, and whenever something gets eliminated, I need to have an extra bond, because otherwise I'm going to be sitting with an unstable carbon. So there's my double bond, and then on this side I'll still have my CH3. And this chemical reaction is already balanced, so that's wonderful. This is an elimination reaction. How do I identify an elimination reaction again? One thing on the left-hand side, more than one thing on the right-hand side. Okay, the next equation now says we must give the balanced chemical equation that occurs when these two compounds react with each other. Now, I'm again going to draw out the structure, because I just feel that it demystifies the reaction quite a lot. In spite of the fact that it does take a little bit longer, I think it's worth it. Okay, so a carbon with 2 H's. I'm going to draw it in the space of number A because it's bigger. So a H. Let's rather not put it over there. It's not going to look balanced. We'll put it like so. Right. Then we are told that we have a double bond. So we draw the double bond. bonded to the second carbon, I've got one hydrogen. Doesn't matter if you put it at the top or at the bottom. This is a three-dimensional figure anyway. And then a carbon and three hydrogens. And reacting with this compound is hydrogen bromide, HBr. Okay. Now, I'm pretty sure that this is going to be an addition reaction. Why? Because I've got a double bond, and that double bond can break, and the carbons on either side of the double bond will have an extra arm which they can use to bond to the hydrogen and to the bromine. So that's exactly what's going to happen here. Let's just write down our product, and I'm going to do that in a different color so we don't get confused. Right, so it's going to be a carbon. Now, I don't know whether the H or where the BR is going to sit, or let's rather put it this way: in the scope of the school syllabus, you wouldn't have to distinguish whether the bromium goes onto the first or the second carbon. So it really doesn't make a difference unless you are told otherwise. So I'm going to put it on the first carbon. Then let's put the bromium on the second carbon, and then CH3. A lovely example of an addition reaction, in this case the addition of hydrogen bromide to a compound called pentene. Right. Okay, so take a look at that for a second quickly before I erase it, because we do have to use the space now for our next question. The thing with identifying reactions and completing reactions is, boys and girls, that it's really like with most things in life, the more you practice, the luckier you get. And fortunately, we're getting a lot of practice today. So, question C now states in words the neutralization of sulfuric acid and sodium hydroxide. Okay, so the first challenge is now you are not given the chemical compound, so you've got to know what sulfuric acid is. And I would hope that by this time in your grade 11 career, that's not too much of a problem. Sulfuric acid is, of course, H2SO4. Sodium hydroxide, NaOH, also called caustic soda. Very, very corrosive, sodium hydroxide. And in fact, most oven cleaners contain sodium hydroxide because it's able to eat through all of the fat and the things that are splashed around in an oven and get it nice and clean. Okay, so sulfuric acid and sodium hydroxide, they are going to neutralize. They didn't even have to tell us that. And the salt that we are going to get is, and I'm just using the next line so that it's not too small, Na2SO4. Okay, Na2SO4, and that is because SO4 carries a charge of 2-, and then, of course, water. Now, I need to just quickly balance this chemical reaction. There's 2 sodiums on the left-hand side, so I'm going to put a 2 in front there, which means that I must then... No, that's perfect. That's absolutely perfect. Yes, let's check that that's right. Okay. So neutralization of sulfuric acid and sodium hydroxide, the products are salt and water. So there's our salt, there's our water. We've taken 2 things with pHs on the extremities of the pH scale. We've put them together, and we've managed to neutralize them to a pH of around 7. Right, next up is the redox reaction between potassium and oxygen. Potassium and oxygen. Now remember, you can use your half reaction table to assist you. Redox reaction between potassium and oxygen. So let's have a look quickly. I'm starting with potassium. I add oxygen. Now, Potassium is in group 1 on the periodic table, and all of the metals in group 1 carry a charge of 1 plus. Oxygen, always in a compound, carries a charge of 2 minus, which means that if I put potassium together with oxygen, oxygen being 2 minus and potassium being 1 plus, this won't be balanced, so I'll have to say K2O. Then I just need to quickly balance this one as well, and I'm going to do that by putting a 2. Let's just have a look. I will have to put a 2 over here, a 4 in front of the potassium, and that's it. That's balanced. Right. Did I even need to balance it at all? I just want to double check, guys. Sorry. I've written so much over this. So what was it again? It was potassium and oxygen, giving us K2O. Yes, that balancing is, in fact, exactly what I need to do, because I've got 2 potassiums on the left-hand side, and I've got only 1 potassium on the right-hand side. Okay. The next question deals still with our previous reaction, and it just now asks us for a part of it. It asks us for the oxidation half reaction. The oxidation half reaction. Now, let's have a look quickly at what did get oxidized. Potassium on its own, charge 0 in a compound, because it's group 1 on the periodic table, 1 plus. So that's definitely the oxidation half reaction. So I've got to say potassium turns into potassium 1 plus, okay, plus 1 electron. In the process of becoming positive, potassium has lost 1 of its electrons. Let's move on to question 1.6. Concentrated sulfuric acid reacts with copper. Name the oxidizing agent in this reaction. So concentrated sulfuric acid reacts with copper. Name the oxidizing agent in this reaction. Now, guys, it is important, I think, to know that most acids are oxidizing agents. It obviously depends on what it's reacting with. So in a reaction between a metal and an acid, the acid will definitely be the oxidizing agent. So the oxidizing agent, you could say sulfuric acid. You could also say the sulfate ion. Either of those would be considered correct. So let's write them both down. Sulfuric acid or the sulfate ion. And I think it would also be acceptable if you just gave the chemical formula of each of those. The next question asks us to write down the equation for the oxidation half reaction in this process. Equation for the oxidation half reaction in this process. Right. Now, what's going to happen is that copper is going to turn into copper 2 plus 2 electrons. How did I know that copper is going to be the one that's oxidized? Well, firstly, I've said that an acid is usually an oxidizing agent, meaning that the acid will actually get reduced. The other thing is, copper in its elemental form cannot be reduced. Copper can certainly not be reduced. It can be reduced if it's copper 2 plus. It can be reduced back to copper. But if it's already at 0, you cannot reduce the copper. So that is how I knew copper going to copper 2 plus 2 electrons. Right. Next question asks us for the formula of the gas that is produced. Okay. Now, I suppose it's probably at this point not a bad idea just to write down the whole reaction. So let's do that. let's say we've got copper and we've got sulfuric acid. And that is going to give us copper sulfate and SO2. So the gas that is produced is SO2. Let's have a look at our next question. Copper is now added to dilute nitric acid. The two reactions on the reduction potential table that are used are given below, and we are given both reactions. Then we are asked, by referring to the given reactions, name the substance that acts as a reducing agent. Now guys, it's important that we remember that the substance that acts as a reducing agent is the substance that gets oxidized. So let's have a look at our oxidation numbers and decide what's happening over here. Right. In NO3 minus, the N carries an oxidation number of 5 plus. Right. However, in NO, because oxygen is always 2 minus, it carries an oxidation number of 2 plus. So what has happened to the nitrogen? It has gone from an oxidation number of 5 plus to 2 plus, so we can say that nitrogen is reduced. Right, so nitrogen is reduced, which means that nitrogen is the oxidizing agent. So nitrogen was reduced, it's the oxidizing agent. However, the question says which one is the reducing agent. So now we need to look for something that gets oxidized. Now the two reactions were written directly from our information sheet. However, I'm just going to write the second one the other way around in a way that makes sense. So we're going to say copper going to copper 2 plus plus 2 electrons. Right, so I'm writing it the other way around because we're actually starting with copper because the question says that copper is now added to dilute nitric acid. So let's have a look at what happens to the copper. We go from an oxidation state of 0 because it's just plain copper to 2 plus. So what has happened to copper? Copper became oxidized, so therefore copper is our reducing agent. Right, so that's our first answer. Name the substance that acts as a reducing agent, copper. The next question says, name the substance that is reduced. Now, if you look at your chemical equation as a whole, like I did beforehand, we already actually know that. What gets reduced? From oxidation state of 5 plus to 2 plus, the substance that gets reduced is nitrogen. And the next question says, write down the oxidation half reaction. So let's have a look again. The oxidation half reaction is definitely the one that releases the electrons, where we go where something becomes more positive or less negative. So the oxidation half reaction, it's very important that you guys write it the same way I did over here, meaning the right way around. That is copper going to copper 2 plus plus 2 electrons. Remember, guys, that when we have an oxidation half reaction, we're always looking for the reaction with our electrons on the right-hand side because we are getting rid of the electrons. Let's have a look at question 2. In question 2, we are given a table showing us different types of bonds. The first bond is a single bond between 2 carbons. Then we've got a double bond between 2 carbons, followed by a triple bond between 2 carbons, then a bond between a carbon and an oxygen, and carbon and hydrogen. And for each of these bonds, we are given the bond length as well as the bond energy. Now, the bond length is how far are these guys apart from each other, and the bond energy is the energy needed to break that bond. They also tell us that a chemical bond is a resultant net attractive force between 2 atoms. Right, let's look at the actual question. From the table, identify factors that will influence the strength of the bond between two atoms. Clearly state how it influences the bond strength. Okay, now let's have a look at any possible trends that we can see. I'm starting off with a single bond where I've got a bond length of 154. Now it appears that the bond length is getting less with the number of bonds. So this is a single bond between two carbons, 2 bonds and 3 bonds. So the first thing that I can say is with multiple bonds, the more bonds there are between the two carbons, the shorter the bond length, right? That makes sense. So let's just make a note. More bonds, and we can perhaps say that we mean by that from single carbon bond to double carbon bond to triple carbon bond. The more bonds, the shorter the bond length, which makes sense. Because if there's more bonds, they are held more tightly with a bigger force. The shorter the bond length. Okay, wait, let's write it here. Point number 1, more bonds equals shorter bond length. And with this, I'm specifically referring to as I go from a single to a double to a triple bond. Right, so that's the first conclusion I can draw from the table, but there's definitely more because they wouldn't have given me all of that information if there wasn't more to conclude about it. So let's go back. Now, we've already said now with more bonds, the bond length decreases. So they're held closer together. What do I see in terms of the trend in the bond energies? I can see that the bond energy increases. So I'm going to add that. Shorter bond length. Okay, so I'm going to write with shorter bond length. The shorter the bond length, maybe in a full sentence. The shorter the bond, the higher the bond energy. And it actually does make sense that if two things are held closer together, closer to each other, that they will be harder to break apart. Now, I've commented on the bond length and on the bond energy for the carbon sequence from single, double to triple bond. But now, it's definitely not a coincidence that I'm given 2 other things here as well. And here I've got carbon bonded to oxygen, and there's a bond length. Carbon bonded to hydrogen, there's a bond length, and then the 2 bond energies. Now, it's clear to me that the carbon bonded to the hydrogen has a shorter bond length and a higher bond energy, right? But now I need to think of a possible reason why. And the reason why is the fact that hydrogen is a lot smaller than oxygen. So hydrogen is a lot smaller than oxygen. So let's put that down there. Carbon bonded to a smaller atom decreases the bond length and increases the bond energy. So it's very important, guys, if you are given a table to make a conclusion from, that you look at the table and make your conclusion from the table. The information is all there, and as long as you just think about it clearly and logically, you will be able to answer it with great ease. Right, so let's move on to the next question, and the next question still deals with this particular table. So now they say to us, study the diagram below. and calculate the amount of energy needed to break the bonds between the atoms in the diagram. So how much energy do I need to blast that whole thing apart? Now, let's have a look at what the sort of bonds are that we're dealing with. Here's a carbon-hydrogen bond. There's a carbon-hydrogen bond. Another one, another one, another one, and another one. So in total, there are 6 carbon-hydrogen bonds. And the bond energy is given to us. It's telling us that the carbon-hydrogen bond energy is 411. So this is going to be 6 times 411. Plus, for the one carbon-carbon bond, that's then ones, times 348. And let's add these two together. And this gives us 2814. And our unit, of course, is kilojoule per mole. So kJ per mole. So this is a lovely extra little question. The information is all right there. You need to just identify the fact that the bonds in this particular compound, this is called ethane, that all of these bonds are actually also in the table above. So you can just go straight from there. Right, so nice question on just some trends that we can spot from bonds. Let's move along then to question 3. And the first question asks us to draw the Lewis structure for ammonia. Now let's just quickly talk about how we draw a Lewis structure again. Remember, you indicate your valence electrons on the Lewis structure. So I'm going to start off with nitrogen. If you are unsure, you can take your periodic table, look at the atomic number, and draw the full Aufbau diagram. That's absolutely fine. For ammonia, I have got 5 valence electrons. 2 of them will be paired, and the other 3 will be on their own. Now, this is quite significant, the fact that nitrogen has a lone pair electron. It's got a big influence on the shape of the molecule. So let's just quickly then draw ammonia, and I'm going to put in, I need to put in the hydrogens obviously. And hydrogen has got 1 valence electron. And let's use a different color. Like that. Right, so there we go. There's our Lewis structure or our Lewis diagram for ammonia. Right, so how do you draw it? Well, you've obviously got to know, firstly, you've got to know the chemical formula because they said ammonia. So you've got to know that ammonia is NH3. Ammonia, NH3 first. So firstly, you need to know what molecular formula you're dealing with. And then you indicate your valence electrons in your Lewis structure. If you have difficulty, you can draw an Aufbau diagram to get the number of valence electrons and to see how they are put about. Right, let's have a look at the second question. Right. The second question asks us, determine the electron negativity difference and the shape of the molecule and use this to explain whether the bonds are polar or the molecule is polar. Now, what we need to do is take your periodic table. The electronegativities is indicated on the periodic table for you. So what I'm going to look at now is, if I just draw it like this quickly, there are my bonds. My bonds are between the nitrogen and the hydrogen. So what I'm going to do is I'm going to look up those electronegativities on my periodic table, and you will find that nitrogen is 3 and that hydrogen is 2,1. So the difference in electronegativity of hydrogen and nitrogen, I'm going to indicate it by saying delta En, meaning the difference, and the difference is therefore 0,9. Okay. Now the fact that the electronegativity difference is 0,9 indicates to us that these bonds are polar. So you will show your little calculation and you will then say, yes, the bonds are polar. Now let me just quickly talk you guys through when is an electronegativity difference big enough to say that the bonds are polar, and let's just look at that scale quickly. All right, so if your difference in electronegativity, so let's call it delta En. If your difference in electronegativity lies between 0 and 1,7, we say that the bonds are polar. Right. If the electronegativity difference is 0 exactly, then the bonds are non-polar. And if the difference in electronegativity is bigger than 1,7, then we are dealing with an ionic bond. Okay, so that is how I knew exactly 0, non-polar. Between 0 and 1,7, we are dealing with a polar bond, and greater than 1,7 is ionic. So big electronegativity differences we usually find when a metal bonds with a non-metal right on the other side of the periodic table, and those of course are called ionic bonds. Remember, when a metal and a non-metal bond, it's an ionic bond, and the bond between two non-metals is covalent. We can also have polar or non-polar covalent. So we are dealing with a covalent bond because both nitrogen and hydrogen are non-metals, but it is a polar covalent bond. Right. Now, the molecule itself will most definitely be polar because it is asymmetrical. So let's write that down. Asymmetrical. It's got the shape of a pyramid, and because it is asymmetrical, it will therefore be polar. And the reason why NH3 is asymmetrical is because of that lone pair that I described to you guys earlier on. So those two electrons, that lone pair contributes to the fact that it's got a shape like a pyramid, like that. It's not symmetrical, so therefore it is polar. Right. Let's move on to the next question. The next question, now we're still dealing with ammonia. Draw a pressure against volume graph to show the relationship between P and volume if an ideal gas is used in this investigation. On the same set of axes, show a possible deviation where ammonia is used. Okay, now guys, an ideal gas is a gas that doesn't exist, firstly, so, but a gas that reacts ideally in all situations. So even under very, very high pressure, under very low temperature, an ideal gas follows the gas laws, we can say. Now let's have a look at what we would expect for volume against pressure. I'm going to start off, because it's a science show, and because it's really important that you guys draw your diagrams properly, I'm going to use my ruler for this one. Right. Okay, so I'm going to put pressure in kilopascal on the y-axis and volume in cubic meters on the x-axis. So firstly, we just need to think of what is the relationship between pressure and volume anyhow. Now, the more the pressure, the smaller the volume, and the bigger the volume, the less the pressure, right? So my ideal gas, I'm going to draw it in pink. like that. Now I'm going to use a different color to draw the graph for ammonia. Now, what is going to happen is that we're going to see a deviation right over here. So at low pressures, it's not a problem. But as the pressure gets higher, my real gas, NH3, is going to deviate. And the reason why is because at very, very high pressures, the particles are very close to each other, and what will happen to a real gas is that it will liquefy. Remember, one of the definitions of an ideal gas, the particles are identical in every way, is the first one. The next one is that there are no forces of attraction or repulsion between the particles. But most times, our normal gases, as long as the pressure is not too high, over here, it'll react just like the ideal gas. But because there are, even if there are weak, intimate forces between the molecules, if the pressure is very, very high, they will be very close to each other, and my gas will tend to liquefy. So what we will be looking at here is, did you guys mark your axes? Right, so did you put labels? Is your shape correct? And you've got to show the deviation of your NH3 correctly on the graph. Right, so just a quick recap on the question. If you want to find out whether a bond is polar or not, you need to consult your periodic table, look up the electronegativity. Then calculate the difference in electronegativity. If it's 0, it's nonpolar. If it lies between 0 and 1,7, it is polar. And anything bigger than 1,7 in terms of difference of electronegativity would make it an ionic bond. Now, to decide whether a molecule is polar or not, you need to look at the shape and the symmetry of the actual molecule. In this case, with NH3, because of that lone pair at the top, it's definitely asymmetrical. So, therefore, the molecule will be polar as well. And then finally was just a little question on NH3 and comparing how gases react in comparison to ideal gases. And remember that the reason why I've got this deviation, it happens at high pressure, and that's because there are forces of attraction between the gas particles. Even if they are weak when they are far apart, when they are very, very close together, it tends to liquefy. Right, let's have a look at our next question. So we are now finished with our bond and molecule shapes, and now we're looking a little bit more at the chemical calculations that might be expected of you guys. So the first question asks us to calculate the percentage composition of ammonia. So still on ammonia, NH3. Now when we are asked for percentage composition, we merely want to know what percentage is ammonia and what percentage is nitrogen rather, sorry, and what percentage is hydrogen within that ammonia molecule. So what you'll have to do is first calculate the entire molecular mass of NH3. Again, for this you will use your periodic table. Fortunately, I happen to know them. For nitrogen it's 14 and each hydrogen is 3, so that is 17. Then I need to look at the percentage of ammonia that's made up out of nitrogen and the percentage of ammonia that's made up out of hydrogen. Now for the 17, nitrogen contributes 14 and hydrogen contributes 3. Right, so let's have a look at the percentage nitrogen. So it's 14 out of 17, which gives me 82,4 82, let's say 82.4%. 82.4%. And then the percentage hydrogen is 3 out of 17. Obviously, the balance must give us 100%. Okay. And that gives us then 17.6%. Percentage hydrogen is 17.6%. The next question now deals with a chemical calculation, so let's have a look at that one. Nice, interesting one. Ammonia is produced in the Haber process. Now, the Haber process is a very, very important chemical process. A gentleman by the name of Fritz Haber actually won the Nobel Prize, not for inventing the Haber process, not for inventing the reaction, but for finding a way to make this very economically viable. Right. So ammonia is produced in the Haber process according to the following equation. So we take nitrogen, we add hydrogen, and under certain conditions, and it really has to be under certain conditions, we get NH3, which is ammonia. Now, ammonia is a very important compound. It's used in a lot of cleaning agents, so it's something that's well worth our while to make. Now, we are told that 21 grams, there's a movie like that, 21 grams of nitrogen and 7 grams of hydrogen are placed in a closed container. And they want to know from us, what is the limiting reagent or reactant? Now, let's just think a little bit about the definition of the limiting reactant. The limiting reactant is that one that's going to be finished first. So even if we've got leftovers of the other, the reaction is not going to happen because I don't have enough of both. Now, to identify the limiting reactant, we need to look at two things. We firstly need to know how many moles of each substance have I got. How many moles of each substance have I got? So I'm going to calculate that quickly. Right, so I'm going to say N is equal to the given mass over the periodic table mass. Right, so I've got I was given 21 grams of nitrogen. The periodic table mass is 28 because it's N2. And let's calculate that quickly. (21) divided by 28. And that's 0.75. Right. So the first thing that I know now is that I've got 0.75 mole of N2. Okay. Now I'm going to have a look at how many moles of H2 do I have. So using the same formula, I'm going to say, well, I'm given 7 grams of hydrogen. So that's 7 divided by 3H2. So that is 7 divided by 6. And 7 divided by 6 gives me roughly 1.66. 1.16 rather, mole of H2. Right. So it is clear to me that I have more moles of H2 than I have moles of nitrogen, but that is not conclusive. You can't say, oh, okay, but then surely the nitrogen must be the limiting reagent because, you know, I've got fewer moles of that. It doesn't work like that. We also need to now have a look at the ratio in which this reaction takes place. Now, If we have a look at the balanced chemical equation, it's very important for this reason that you balance the equation if it isn't balanced already. For every 1 nitrogen, 1 mole of nitrogen, I need 3 moles of hydrogen, okay? So if I'm going to use up all of my nitrogen, I will need 0.75 times 3 moles of hydrogen in order to react with those. So that's 3/4 times 3, and I don't have nearly that. I don't even have double. So the limiting reagent is nitrogen, because is hydrogen, because for every 1 nitrogen, I need 3 hydrogens. And if I'm going to use up all of my nitrogen, I'm going to need 3 times as much hydrogen, which I don't have. So that is why your hydrogen is your limiting reagent. So please, guys, yes, you need to compare apples with apples. So you need to firstly make sure that you're comparing the moles, but you then need to look at the ratio in which they react. We can also see this another way. We can say, we can say that if I need to know exactly how many nitrogen I need for the 1.16 mole of H2, I can divide 1.16 by 3. And I will see that I need a lot less nitrogen than 0.75. So the limiting reagent is hydrogen. Right, let's move on to the next question. The next question asks us for the number of moles of the reactant that is not used up. Now what I'm going to do is I'm just going to rewrite my balanced chemical reaction right over here. So I've got N2 plus 3H2 giving me 2NH3. Okay. Now, the ratio over here is 1 to 3. So for every 1 nitrogen, I am going to need 3 hydrogens. Then I'm going to write in here, okay, I know that I'm going to use up all of the 1.16 moles of my hydrogen. And why do I know that? It's because hydrogen is my limiting reagent. So now I'm going to calculate, I'm going to put an X over here. I'm going to calculate how much N2 do I use, okay? And once I know how many moles of N2 I use, I can subtract it from how many I had in the beginning. So this is an easy way to solve most. So I'm going to cross multiply, and I'm going to say 3x is equal to 1.16. And I'm going to take out my calculator again. And I'm going to say 1.16 divided by 3. And let's do it as a decimal. I am going to use only, I'm going to round off now to 2 decimals, 0.39 moles of my nitrogen. So I can say I use 0.39 mole. And therefore, now I'm running out of space over here. Let's just make some space. So I use 0.39 mole. So therefore, left over is 0.75 minus 0.39. 0.75 minus 0.39, and let's get our calculator again. 0.75 minus 0.39, and I am left with 0.36 moles of nitrogen. Let's write that in a different color. 0.36 moles of nitrogen. Right. Question C asks us now to calculate the number of molecules of ammonia that is produced. The number of molecules of ammonia that's produced. Now, before I can calculate the number of molecules ammonia produced, I'm first going to calculate the number of moles ammonia produced. And I'm going to write down my balanced chemical equation once more. So this is N2 plus 3H2 giving me 2NH3. So I'm not going to worry about the nitrogen because that's the limiting reagent. I'm going to say the ratio is 3 to 2. And I know that I have got 1,16 moles of hydrogen at my disposal. Now I want to calculate how many moles of ammonia is that going to make. And once again, I put an X. Then I cross multiply. Now I know I've got my ratios right. And I get an equation that says 3x is twice times 1,16. 3x is 2 times 1,16. So x is 2 times 1,16 divided by 3. And that is then the number of moles, okay? Not molecules, moles. Now the question actually asks us for molecules, which means that once you have obtained your number of moles, you will multiply with Avogadro's number. So multiply by Na. Right, I need to get my calculator out here. 2 times 1.16 divided by 3. And the answer is 0,77. 0,77 mole. So 0,7 multiplied by Avogadro's number. Right, so 0,77 is then multiplied by Avogadro's number, 6,02 times 10 to the power 23, and we're going to write down our answer, 4,6 times 10 to the power 23. So that's 4,6. Our final answer, 4,6 times 10 to the power 23 molecules. Right, so this has been a really, really nice question. What I've really enjoyed about this question is we were asked all sorts of things. The question theme was ammonia. We were asked about the bonds. We were asked about the shape of the molecule. We were asked some properties of gases. And then finally, we were asked to do some chemical calculations, some stoichiometry. Right, let's have a look at question 4. Question 4 and question 5 deals with chemical systems. So that means we are talking here about either the atmosphere or the lithosphere. And in this case, it's the atmosphere. So let's quickly read through. CFCs are non-reactive molecules that are used as propellants in aerosols and coolants in refrigerating systems. These molecules decompose ozone in the atmosphere. When CFCs in the atmosphere are exposed to UV radiation from the sun, reactive chlorine atoms are emitted. These are called radicals. The chlorine radicals acts as a catalyst to break the ozone down. Now, it's important that we at least mention that I was in the beginning of my high school career when deodorant cans and things started coming out that said CFC free or ozone friendly. But the damage by then was already done. Right. Now, let's have a look at the questions that we have to answer. Usually, these questions are relatively straightforward. Why is it important that we control the emission of chemicals that break the ozone down? Why do we need an ozone layer? Guys, because the ozone layer protects us from the sun's UV radiation. We will all be fried within minutes if the ozone layer wasn't there. So we need to protect our ozone layer in order to protect ourselves from the sun's UV radiation. Right, let's have a look at the next question. Where do we find the ozone layer. Now, in this case, it's not good enough just to say up in the sky. It is between 20 and 60 kilometers above the surface of the Earth. So it's high. It's higher than, much higher than where planes fly, for instance. It's far away, but that protection is still very much needed. Right, let's look at question 3. Write equations to show and explain how ozone molecules are made. Write equations to show and explain how ozone molecules are made. Right, let's have a look at these equations. Firstly, let's start with oxygen. So oxygen, which is of course a gas, if it is exposed to UV radiation, can break up into oxygen on its own, right? Oxygen molecules absorb UV light from the sun. This then breaks them into 2 highly reactive radicals. Now this 2O is a highly reactive radical. The oxygen in the atmosphere, together with one of these radicals, then gives us O3, and of course O3 is the ozone gas, which protects us from the sun. Right, let's have a look at our next question. Still on the carbon fluorocarbons, write chemical equations to show how CFCs break ozone molecules down. Okay, so let's firstly write down the equation or the chemical formula of a CFC. CF2, and these are, in this section there's not a lot of chemistry, so I would say that these 2 sets of chemical reactions you definitely have to learn. So CF2, Cl2, that's our CFCs, are exposed to UV radiation from the sun. They then break up, and once again we've got a radical situation on our hands. There's a radical and there's a chlorine radical. And it is then this chlorine radical that does all the damage to the ozone layer, breaking it into ordinary oxygen, which doesn't offer us any protection from the radiation of the sun at all. So this is O2, and that is a gas. Right, so that very quickly, question 4, dealing with the ozone layer. As I said, guys, there's not a lot of chemistry to it. You do need to know how it works. You need to know why we need an ozone layer. You need to know where it is. You need to know what it is that's breaking down the ozone layer, and so forth. We have consolidated a couple of topics: our types of chemical reactions, our chemical bonds, calculations, and then also our chemical systems. Do tune in again next time.